Today's specific lecture, this first lecture here on physical equilibria, has to do with vapor pressure. And in fact, what we're going to do is spend the rest of this lecture looking at that very single experience. And the experience is an easy one to describe. It's this thing right here. Here's a can of Coke. And sitting inside this can of Coke is a particular liquid, water with some stuff mixed into it. Although you can't see it, sitting inside this can of Coke is a head of gas, a head of vapor. And that vapor has a certain pressure. There are certain conditions that prompted this particular vapor pressure to have been achieved sitting inside here, and that's what we're going to want to explore, first in a qualitative way, but then later in a quantitative way as we develop this thing called the Clausius-Clapeyron equation. The Clausius-Clapeyron equation is a wonderful equation that we can derive that when it's all said and done will actually tell me what the pressure of this head of gas is above this liquid down below it. When we talk about vapor pressure, we typically talk about it as in a device like this, which is sort of simulating that can of Coke I just showed you. Here's the can of Coke, the water that sits under here, and notice above it I have some vapor sitting up here. This is the vapor of the water. This is what I want to know the value for. And as I stop and I ask myself about it, I have to ask what the physical phenomenon is that's responsible for the fact that I have that head of water vapor sitting up there. Well, if you were to zoom in really far and look at it, you would see that vapor pressure is actually a surface phenomenon. So here's my water molecule sitting here. They're held together because of intermolecular forces, hydrogen bonding, for example. And you can see that the gas vapor up here is actually not static. It's a very dynamic, very fluid sort of thing that's going on. There is a water molecule, for example, which has decided to deposit itself down on the surface. And there is a water molecule that has decided to go up into the gas phase. And this is where the idea of physical equilibrium comes into place. This is a physical equilibrium process once I get to the point where the number of water molecules hitting the surface is exactly equal to the number of water molecules going up into the vapor phase. So in much the same way that I showed you A and B in equilibrium with it before, here's my equilibrium here involving vapor pressure. Water is a liquid in equilibrium with water as a gas. The question is just exactly what is that pressure we have up there? And that's what we're going to try to evaluate in today's lecture. So now that we're looking at this ratio of the number of gas molecules to this liquid here, we have to ask ourselves what physically is going on. The first thing that we notice is that this is a surface phenomenon. Notice that the molecules most likely to make it into the vapor phase are the ones sitting up here on the surface. Now you might say, is it possible for molecules down here to get up above? Well, no, they've got to get through all of this to get up here. The only way I can imagine this happening is if we were to put an enormous amount of heat into the system so that we could create these little pockets of vapor sitting down inside this system here. Oh, that's what boiling is. See, if I can heat my system up enough, I might be able to create a situation where sitting down in the volume of this liquid, water in this case, I'm creating vapor. But that's boiling as a phenomenon. I'm not interested in boiling as a phenomenon. I'm only interested in the surface effect, the one that's associated with creating that head of vapor that sits up above the surface. Understand also that this isn't about evaporation, because if it was, I wouldn't be talking about this kind of steady state amount of vapor sitting up here. The water molecules would be leaving and disappearing. I'm going to be putting a top on this, like in my can of Coke, so that I can establish an equilibrium. Notice that I can't establish an equilibrium if my gas molecules are constantly leaving the system. So vapor pressure must be a closed volume measurement that we want to talk about. So just to summarize this sort of qualitative feel for this, vapor pressure must be a surface phenomenon as opposed to something that takes place down in the liquid. And it's something that must take place sitting inside a closed volume.